So today we're going to talk about three things. We're going to talk about differential equations, terminal velocity, and then setting up differential equations. Cool. So first thing, what is the differential equation? So looking at this nice word, I see the word differential. Oh, it looks like the word derivative. And a differential equation is just any equation that contains a derivative. So I want you to look at the however many, A through G below. And I want you to think about which of these equations are differential equations. Go ahead and pause the video, take a guess, and then check back in. Okay, so looking at this, again, a differential equation is just anything that contains a derivative. So A has a derivative. Let's see what else. B has a derivative. D has a derivative. And G has second derivative, double derivative, but all derivatives. Cool. So what I want to think about right now is what is the net force equal to if acceleration is constant? So we know Newton's second law, F net equals ma. So now what we're going to look at today is cases when acceleration is not always constant. So if it's not constant, we know that acceleration is going to change depending on velocity. So that is going to be dv dt. So keep in mind acceleration is the derivative of velocity with respect to time. And this is what we're going to use a lot of today instead of, or in addition to, just mass times acceleration. Okay, so now we are going to talk about terminal velocity. So terminal velocity occurs when an object is falling through the air and experiences no acceleration. So this is when all the forces are balanced. And if we think of an object falling through our air, like or a skydiver or something like that. So we have our friend the skydiver. Great. He's so happy to be flying through the air. Great. So if we look at the skydiver, forces acting on the skydiver, we have gravity. Let me just drop force of gravity on there. And then there's also going to be air resistance or air drag. So we can call it force of air resistance, force of drag, whatever you want. So let's think about factors that affect air resistance or drag. So definitely like the shape of the object, like the area, cross-sectional area of it, density of air, the velocity of the person. If they're going faster, they're going to experience more drag. All those things will affect their drag. Let me just also write down the definition for terminal velocity. So this occurs when a falling body experiences no acceleration when all the forces acting on the body are balanced. So in terms of equations for air drag, a problem will pretty much always give us like what the equation is, and it'll depend different things. So it'll often be some constant times the velocity, so it could be like kv or cv or whatever, or sometimes it is some constant times v squared. So you'll see both of these equations used, and sometimes there'll be like a different variable for k, etc. Cool. So let's go ahead and look at the part below. So draw the forces on the skydiver at the times indicated below. And let's make sure to draw our vectors to scale. So go ahead, pause the video, do this on your own sheet of paper, and then check back in. Okay, so at t equals 0 seconds, so that's right as the skydiver is starting to fall. So he or she is not going to experience any air resistance. It's just going to be gravity initially. Great. So now at 3 seconds, gravity's still there. Gravity's always there. I'm just going to draw gravity for all the people. Gravity's always stays the same size, unless you're like losing mass or something crazy. Cool. 3 seconds, they're going to experience a little air resistance, so I'm going to call it F air. Cool. 6 seconds? Well, let's see. They're going to go faster, so they'll have a little bit more air resistance. And then at 9 seconds, or terminal velocity, this is when gravity and air resistance should be the same size, so that the net force acting on the person is just 0. Okay, so now we're going to go ahead and solve an AP Physics problem using everything we just learned. So again, I encourage you, go ahead and pause this video, write it down, solve it yourself, and then check back in. Cool. So after you've done that, let's look at it together. So we have a rubber ball of mass m, so this is it right there, and it's dropped from a cliff. As the ball falls, it is subject to air drag, a resistive force caused by the air. The drag force on the ball has magnitude bv squared, where b is a constant drag coefficient and v is the instantaneous speed of the ball. The drag coefficient b is directly proportional to the cross-sectional area of the ball and the density of the air and does not depend on the mass of the ball. As the ball falls, its speed approaches a constant value called the terminal speed. On the figure below, draw and label all the forces on the ball at some instant before it reaches terminal speed. Sorry about that. Great. Okay. So now I'm back. Okay. So let's go ahead and draw. Oh, I love drawing free body diagrams. There's nothing more fun. So one little thing I just want to keep in mind for these problems, we're going to always define, unless the problem says otherwise, the downwards direction as positive. So keep that in mind. Unless noted, downward direction is going to be positive. So we know gravity is always there. If something has mass, gravity is there. I'm going to go ahead and label what it is. The mass is m, so it'll just be mg. Cool. And then air drag. So that is resisting its motion. So it is going to go the opposite direction, upwards. So I'll call it F drag equals BV squared. Cool. One thing I should be careful of, if in some instance before it reaches its terminal speed, should drag be the same size, more or less than gravity? Well, if it's before terminal speed, it should be less than gravity. So I should have drawn that arrow a little smaller. Sorry. There we go. That's better. Cool. So now let's go ahead and look at B. So state the magnitude of the acceleration of the ball of mass m increases, decreases, or remains the same as the ball approaches terminal speed. Explain. Okay. So as ball approaches terminal speed, the drag force, let's write this all down, as approaching terminal speed, F drag will increase. So if F drag increases, it'll get closer in magnitude to Fg. So F net gets really, really close to what number? Oh, 0. So F net decreases. So if F net decreases, acceleration will decrease as well. Okay, so now what we're going to do is we're going to do part C. We're going to write but not solve a differential equation for the instantaneous speed of the ball in terms of t, the given quantities, and fundamental constants. Okay, so cool thing is, we basically already know how to do this. So let's go ahead and set up F net. And again, we define the positive direction to be downwards. So the forces acting on this ball are Ft and F drag. Oh, and we already have a nice free body diagram to use that information from. Again, I'm getting that all from here. Great. So Fg is positive and F drag is negative. Cool. So now let's put in F net is what? MA. Fg, we know in this case is mg. Sometimes drag, it'll define it as negative bv squared or positive bv squared. Who knows what it is? But I always, when I plug it in, just worry about the size of the two forces. Do I need to add or subtract Fg and F drag in this case? In this case, they need to be opposite signs, so keep that in mind. It's kind of like string force. Great. So we have mg minus bv squared. So now we need to turn into a differential equation. So if there's a differential equation, we know, and we already know the situation, acceleration is not constant. It's going from g meters per second squared to 0 in magnitude. So acceleration we can rewrite as dv dt. But everything else just stays the same. So this right here is going to be our good old differential equation. Okay, so for part D, our last part, we're going to determine the terminal speed, vt, in terms of the given quantities and fundamental constants for this object. So terminal speed, that occurs when F net equals 0. Great. So if we set this up, we know F net is equal to, we already set our two forces, it's equal to Fg and F drag. And I should say when F net equals 0, acceleration is 0 meters per second squared. Great. So we can just plug in here for F net. We know that's just 0. So then we have mg minus bv squared. Cool. So now we just get to solve for v. So do some fun old math. Oh, I love math. Mg over b. And then take the square root, and we got it.